let's discuss how to calculate work done using an equation. So we are going to study how to calculate work done due to the individual force, one single force. And that force will have to be constant throughout the journey, and the displacement, the journey, have to be in a straight line. No turns, no bend, no U-turn or anything, just a straight line motion. So work done under this situation of a constant force and a straight line displacement will be just the scalar product of the constant force exerted on the body, F, and the straight line displacement that occur to the body, S. So because it's a scalar product, we should expect the equation to be work done equals to dot product of force and displacement. As you can see, because it's a dot product, we call it also as scalar product. So you can see the product of these two things will be a scalar quantity. Therefore, you see no arrow for work done. So work done here is a scalar quantity. It only has magnitude. It has no direction. So let's try to apply this equation here in an example. Let's say today here I have a block and I place it on some kind of floor. Okay, then me being too boring, I exert a force of 5 Newton onto the block to the right. So I push the block using a force of 5 Newton to the right. And because I'm pushing the block, then the block experiences a displacement to the right. Let's say I push it to the right, the block was initially not moving, then it moved to the right because of my push. And let's say it moved for a distance of 10 meters. So now let's say you want to determine what is the work done by me, by this force over here. So what can you do is, if you want to find the work done due to this force, or you want to find the work done by this force, what you can do is you just use the formula that we discussed earlier. So you take the force and conduct a dot product with the displacement that occur. So, well, F dot S here is a dot product, so we have to relate back to what we learned in chapter 1. We learned in chapter 1 that for dot product, if it's A dot B, then it's equals to AB cos theta. So this A here will be the magnitude of vector A, this B here will be the magnitude of vector B, and cos theta, this theta here will be the angle between vector A and vector B. So if this is a situation for a dot product, if we use it on this work done situation, this will be equivalent to Fs cos theta, where F is the magnitude of the vector F, S is the magnitude of the displacement S. Cos theta, then this theta will be the angle between vector F and vector S. So we are interested in these two vectors, the force vector and the displacement vector. So for a dot product, what we do is we bring the tail of both vectors to the same point. So let's do that. We bring the tail of both vectors to the same point, then take it as F and S, and now we will conduct our dot product. For the magnitude of force, we know that is 5 Newton. The magnitude of displacement is 10 meter. That one is very straightforward. We just get it from the situation. But what about theta? Theta is the angle between vector F and vector S. We know that if vector F and vector S are in the same direction, then the angle between them will be 0. Then as it gets not in the same direction, then you approach 90. Then if you go in towards the opposite direction, it approaches 180. You look at the angle in between the two vectors. So in this case, they are in the same direction. So the two vectors here has an angle of 0 degree between them. So let's substitute. F we substitute 5.0, S we substitute 10, cos 0. So this is the angle between vector F and vector S. We know from our trigonometry lesson that if it's cos 0 degree will be equivalent to 1. So in this case, we get our answer as 50 Newton meter. Cos 0 here represents the maximum value that you can obtain for a cosine function. Okay, cosine ranges between 1 and -1, right? And cos 0 will be the maximum value that you can get. In this case, we can see that if the force and the displacement are in the same direction, the work done that you obtain will be maximum. And as your angle increases, the work done that you obtain will decrease. Okay, remember dot product, remember the idea of parallelness. The greater the parallelness between the force and the displacement, the greater the work done that we will obtain. So work done has a unit of Newton meter, but because we know that work done can be related to energy, which we will discuss in future videos, therefore we also give them a new unit, which we name it by joule. So we can change it to a symbol J to represent the unit for energy, joule. So the work done by this force, or work done due to this force, is 50 joule. Okay, so let's study deeper. What does this 50 joule mean? Well, this work done here is due by F. The work done is done by F. And this force here, as I mentioned just now, is because I'm boring and go push it, right? So this force is exerted by me on the block. So if I know this work done is by this force, and this force is exerted by me on the block, then we can know that this work done is done by me on the block. It's work done by me on the block. So why is this important? Because work done here is related to the transfer of energy. So what does it mean? It means that 50 joule that we calculate over here represents the energy that is transferred from me to the block. So if I do 50 joule of work on the block, that means 50 joule of energy is transferred from me to the block. And that's the idea of the work done that you have calculated here. But of course, what kind of work, what kind of energy, whether it's kinetic or potential energy, we'll discuss that further in the future videos.